My name is Dr. Mwitende Gervais. I'm from Pivot Access, is a infrastructure and software company here in Kigali, and Rwanda Polytechnic is a polytechnic government polytechnic in Rwanda. My work is titled Lightweight Authenticated Key Agreement. When we talk about key agreement, is the key that is used in cryptography and cybersecurity. That's the field. When two entities want to communicate, they securely, they can share, they can compute the key in order to encrypt the sensitive information during their communication. So authenticated key agreement protocol, of course, as I was saying, involves the participation of two or more parties that want to communicate in a secure manner. So they can share the public parameters and compute the secret key that is going to assist in encrypting when they want to send sensitive information between them. So in that way, the parties can authenticate each other and encrypt the message. There is an layer of application when we are using the key agreement. For example, in banking, in health, when a patient wants to submit information to the hospital, he needs to encrypt his sensitive information and submit to the server. That is conventionally, but generally, PKI, or public key infrastructure, that is of course managed by governments, can provide authenticated key agreements. But in this traditional way, the PKI only can provide the full key agreement, which is a problem because it is managed by someone else instead of being managed by the owner of the information. So we want also to introduce a decentralized or blockchain system, because in our work we used a decentralized system. Decentralization means that there's no central server. There's no need for central server as we used to do in a traditional way, and no one has control over the data, which is okay, because in that way there will be an agreement when someone wants to use information or to receive or to send information. So also in decentralized system, there's persistence, because transactions are validated and honest miner do not admit invalid transaction, which means there's no possibility to delete information from a decentralized system. There's also anonymity, which means there's no level. No one will know the true identity of the nodes in the decentralized system. Auditability also, we can track what is happening in the decentralized system. So we can also talk about the blind signature. The blind signature is the digital signature as other digital signatures, when the signer delegates his power to someone else to sign on his behalf. Of course, the original signer and verifier can verify and distinguish the normal signature and the blinded signature. It is used particularly for user authentication as other digital signature, and of course for verification of whom has signed the documents. Here we can see the steps of how the blind signature is made. The original sign will delegate the power to the proxy. Then the proxy can verify on his turn if the delegation is really true. Then he can send to the signer. Then the signer, after signing, he can send it back to the proxy, and authenticated server will be managing the signature, and the receiver can verify from the authenticated server the signature, and the message can be sent in that way. Now we can also talk about the certificateless authenticated key agreement algorithm. In certificateless is different from the PKI that we all know, because in certificateless the PKI will not manage the entire key agreement as we used to do. The PKI, in that way, we call it the KGC, Key Generation Center. In that way, will not generate the full key agreement for users. Instead, the PKI in that way will generate half of the key for users, and users will generate their full key on their own. This avoids what we call the key escrow problem, because once the PKI generates the whole key, there's a level of the identification and transmission of information of users, because the PKI manages all the information for users. We have 6 algorithms in certificateless. We have setup, we have partial private key extract, we have secret key value, we have set private key, we have set public key, we have also the generation. The last step is to generate the key agreement for users. When data owner sends the data to sorry. I think there's something wrong. Sorry. Yeah, there's problem statements. The problem here, want to avoid a single point of failure because we introduced the blockchain or decentralized system. Also want to create the heavyweight security protocol for of course, for small devices, because Internet of Things and sensors, they are source constraints devices. We need to compute a protocol that is going to run on small devices. That's why we want to compute the small protocol or lightweight protocol for this kind of devices. Also, there's a problem of weak management of conventional certificate issuance. As I was saying, the PKI generate keys for users. In that way, there's a problem because the PKI can have control over users. So also some important security features such as distinguishability and linkability will be provided by the protocol. In that way, it is very important that a lightweight certificateless authenticated key agreement protocol is needed to secure a transmission in a decentralized environment. This is our system model. User A and KGC and user B or application server will generate the secret key, but KGC in that way will not generate the full key as it is done with the PKI. In this way, there will be partial private key on one side from KGC, and the user will create his full key. He will select a secret number, then he creates his full key. The same to B. Then after the proxy signature will be created among these two nodes, user B and verifier node V. The communication can be established between other nodes in a decentralization way. So we can see what's happening with the concrete construction of our protocol. As I previously mentioned, there's a setup. In setup, there's a creation of public parameters. The KGC select additive group G on prime order Q, and the pay is said to be a generator of the group. Also, there is a generation of a master secret S from the group Z to calculate the PPAP, which is a public master public key. This has to be public because when you send public parameters, the dedicated receiver can verify whether the source of the information is correct. Also, select hash functions. In our case, we're going to use two hash functions, and the creation of public parameters as F, and the group G, and pay as the generator, and the PPAP as a public master public parameter. Also, we have two hash functions. There's also the creation of partial private key. As I was saying, KGC takes the input S, and it can compute the equation, and this equation is would be a partial private key. The KGC will send it to the user A, and user A user A will compute his full private key. So the equation here, the user A verifies whether the partial private key is valid by computing the following equation. Then he can, in his turn, select secret value and randomly set an algorithm that is going to create the full private key for his own. In this way, one part of the secret of the key agreement is created by KGC, and another part is created by the user himself, and the user himself will compute the full private key. Now, here we simply have the correctness. After when the user A selects A, he can compute the equation by computing the generator P with the A. Of course, A is not known, and send the message ID to B. In return, the user B select B and compute TB as the secret and send a message to A. Both A and B can compute the secret as the following. KA is the key computed by user A, and B computes the secret key of B. Now we want to verify whether the two keys are identical, because once they are different, they can one cannot decrypt the information sent by A. Once they are equal, therefore B can encrypt information sent by A. Otherwise, the information sent by A will not be seen by B. So the correctness is there. Ka is equal to these equations, and Kb is equal to this equation, which means our algorithm is correct because Ka and Kb are equal. In that way, user B can decrypt information sent by A, and A can encrypt information to be sent by B, which will be in turn getting the identical key agreement. We call this key agreement K, and the established session key is equal to hash function 2, which is equal to ID of A, ID of B. Of course, the equation computed by A, and the equation computed by B, and also the session key. So the correctness is perfect. In that way, we are sure that A can compute information, can decrypt information sent by B. So simply, our algorithm it looks like this. We input identities of users. We also input public parameters, as I said. There's a computation of this equation, Qi, Ri, Hi, and Si, and the output is the key agreement that was created by KGC to A and KGC to B. So user randomly select UI, compute DI, compute XI. A session key is computed as follows. User A selects a secret value from set Z and compute TA, send his identity to B, and B compute in the same way. We end up by having the session key of A that is equal to B, as you are seeing in this algorithm table. But this does not mean that we're going to have to remain with the same key every time when key and A and B want to communicate, they will be computing the key agreement. We also adopted the proxy blind signature, as I was saying. We have the steps. They are power of delegation in the first step, which is going to give the power to the proxy. In the first phase, we call a proxy generation. Then proxy will compute QP. In the second phase, the proxy delegation phase, the signer B will send to proxy to verify. Then we have verification phase, and there's also proxy signing phase, which computes zeta equal to TG and send it to verifier. In the second step, verification phase is verified by V, which computes the following equation, which is omega equal to HBG plus JQP concatenate a message M. Therefore, we will end up by having the blind signature, which is equal to this equation, and we want to check whether the proxy blind signature holds if omega is equal to J. Also, we use the same method model of verifying whether this equation HBG plus JQP concatenate M is equal to H alpha concatenate M. If they are different, therefore, they cannot verify whether the signature is from the right source. So the correctness is okay because these two equations are equal, which is verified here. So we have designed a protocol, an AKA protocol that is going to provide the following functionality, security functionality. It provides key escrow because KGC create half of the key. There's also distinguishability between whom is sending the data, and linkability because you cannot trust the source of the information. There's also the strong undeniability as a security features. Also, to provide the decentralization because we have used the blockchain model. The comparison based on computation cost, we have found that when we compare with the with other four recent protocol, we found that protocol is lightweight compared to the previous four because we found that our protocol computed for time point multiplication. Also, it computed two hash functions, and user B on user R. The same on user B is for point multiplication and two hash function. Also, our protocol computed sent the message that is made of two identities and plus 2 point in Z in set A Z. By concluding, we designed, of course, we designed an authenticated key agreement between A to ensure the secure communication. It provides the key escrow prevention, verifiability, consensus, and strong deniability. Also, proxy blind signature was used in the decentralized to provide anonymity. And the analysis of our protocol was made in a random oracle model, because random oracle model is a model where a user can play with an attacker by sending a message and looking at the reaction of the attacker. Also, attacker reply to the message and the user reply to the message. In that way, we found that a random oracle model is better for this analysis of our protocol. I thank you very much. If there are questions, you can ask.